to share what you've come up with, and let's try to get down some idea now, some properties of what straightness is. Because, you know, the straight line is one of the most basic notions in, I would say, in all of mathematics, but of course I'm a geometer. But, you know, maybe number is, other people would argue that. Okay.
What's the point? That's my other role, actually.
Yeah.
Okay, so how about this group over there? What did you? What's the one or two things that stood out for you that you came up with?
Well, I guess we tried to answer the two questions. How do you make a straight line, and how do you check if it's straight? And we decided the easiest way to make a straight line is to fold a piece of paper.
Okay. Okay. And now fold paper. Now,
And then mathematically, we said you were doing a mirror reflection.
Okay.
The line of the fold would be straight.
okay. So that's important. That straight lines have reflection symmetry. Reflection in the line. Symmetry. Okay, so that's.
How do you know it's a straight line? How do you know it's a straight line?
It's our intuitive understanding.
Well, now, see, what we're trying to come up with is, you know,
How far back do you think?
we're trying to say, you know, what it is that straight means, and this does seem to be one of the things that it means, that there's the two sides are the same. Right? You know, that there's this balance of the two sides of the line. If they're not the same, then we wouldn't call it straight. So in that sense. Now, none of these are going to, you know, we're not talking about the same as getting a formal definition. Okay, so that's great.
Just a point about the same. I think when you fold a piece of paper, the two parts may be different areas and so on, but the place right where they meet, clearly they're the same right locally there.
Let me ask
Shape.
something.
Yes.
How would you tell if that line was straight? How would you check if that line was straight? I know how I would, but...
No, that's how that was the question.
Okay.
We asked the question, you give the answers. What is this?
I look at it at the edge
Uh-huh.
and
Good.
see if it starts looking like a point. I
Good.
can tell that it wobbles. Or
Great.
It's not a point when I look at it at the edge, so I know this line's not straight.
Good.
Okay, so that's another
That's
one
a good way to
that we actually use is sighting along the edge, and you know people do use that. And there's an assumption what that
There is an assumption.
Light travels.
right. So there the assumption is that light travels in a straight line, which it doesn't, of course. And but it does, you know, for in a homogeneous medium and for small distances it works. But like, you know, when the sun gets out here and hot this afternoon, you'll be able to see that doesn't work at all, because when the heat builds up over the sidewalks, you can see the fact that light isn't traveling by straight lines. Or if you stick a straight stick into the water, and you'll see it doesn't look straight. So, but still, sighting is something that we use a lot, and that's one of the assumptions about one of the assumptions about light in the physical universe, away from you know, the so-called empty vacuum, which there is no such thing, but still approximately that, assuming that things go in a straight line. But yeah, so we use it, but we have to be very careful because light doesn't always go in a straight line. But yeah, but sighting along is something that people rely on. And when people are lining up fence posts or something, you know, they just do it by sighting. And I wanted to point out that this folding thing is something that fine cabinet makers once taught me about doing. If you take two boards, you you want to make them straight, because you want to put the boards together, right? You're going to glue them together to make a wide tabletop or something. The fine cabinet maker that's doing things by hand rather than using machines would put the two boards like this and plane them until they were as straight as the cabinet maker could get by eye, with sight of them, until they're as straight as the cabinet maker could tell, and then check it by opening the boards up like this, sort of the opposite of folding, unfolding, and then checking to see whether there's any light shining through. If there's light shining through, well, then that's a low spot. You mark those spots, you go back down, and you go some more plane. And that's a very accurate way. It's more accurate than sighting. The problem with sighting is that farther, our eyesight, the part further away is a little fuzzier than the part closer in. But it works nice for lots of things. But fine cabinet work. This folding things. Okay, so we got some. So let's.
Oh, we thought if we picked 2 points and pulled the string taut, like we would for a garden or something.
Chalk lines, building houses.
Stretch
One
string.
line, your wallpaper.
Okay, so so this is, carpenters use this a lot, stretch string. And both horizontally stretched string with chalk on it to mark where the string went, or a plumb bob, when you're want to get a straight vertical line, just hang a weight on the end of the string. So that's now, what property of a straight line is this exemplifying? So it's the shortest distance. So when it was been pounded into us in school, at least was me, and I assume it still is, that short line is the shortest distance between 2 points.
Straight.
Sorry. What did I say? Short line. That's straight line.
No, that's a railroad, the short line.
Straight line for sure.
That's right.
It's also using the fact that somewhere in the middle, the two forces from the two ends are balancing. They balance it. They're in the same direction.
Right. Okay.
There's a local thing happening
On the string.
inside the string.
Right. Yeah, right. And that's one of the reasons why you use a string and not an iron bar or something.
For a chain, heavy chain.
Yeah, right. Or a rusty chain, say. Something. So you need something that's flexible so that it will balance the forces and the mounts. Okay. Yeah, okay. So in fact, we could, that whole thing about the balancing of the forces, there was a, well, it'll come up. I know other groups had that. But
We had a type of permutation on the third one, is that if you have any 2 points, straight line is all the points that are equidistant from both of those 2 points.
okay. So,
Too hard. We don't know where they
okay. So the straight line is a set of points equidistant between these 2 points. And so in fact, this is a way of actually, if you have a compass, you can use this property to actually construct points on the line. So this is something that we don't really think about so much because we use straight edges so much, is that it's difficult to construct a straight line using, if you don't have a straight edge that you're comparing it with. Whereas a circle, you can construct an accurate circle very easily. Right? I mean, all you need is anything rigid. It doesn't have to be straight. And you pin one part of it down. Where's an example right there? I mean, just think of my arm. Here it is. Right, okay, yeah, right. There's no reason for this to be, it doesn't have to be straight, it just has to be rigid.
Umbrellas.
A circle.
Not good.
But you can use a compass to construct points on a as many points as you want. Okay.
But
And
you could also then, if you had a straight line test, whether it was straight by trying to produce all those points.
right, right.
Yeah.
Or at least the same pair of points all the time.
That's right, that's right. Or different ones if you wanted to. Yeah.
Most of these only work for short straight lines, though.
What?
Most of these only work for short straight lines. You can't straight line between New York and Chicago.
No.
That's a good question.
Right, right, that's right. Yeah, all of these.
As you know, if you ever tried to fly from New York to Chicago.
Okay, great. So we got that one, this group?
We use the folding paper, but we also use the last one to show why our folding paper was a straight line. Because if you fix 2 points on it and then pull out, you're doing it in a perpendicular bisector to show why the folding paper has to be a straight line.
Okay, okay. Yeah, so that's one way to get this. If you fold the paper so this point goes on to this point.
Right, just fix it, yeah, and then just stretch it out.
Okay, okay, that's nice. That's nice. Good?
Well, our group did two things. One, we looked at the shortest distance properly. We can focus in on that. And the other was,
The tricycle?
yeah.
Yes, yeah.
If you ride a tricycle and you keep your arms fixed and only move your feet, and you never come back to the same place, you're traveling in a straight line.
Or you fell off the end of the.
But you can't be, I mean, it has to be on a plane. Big plane.
You take your tricycle on the plane? or-
Yeah, similar thing, so, yeah, okay, but that's now, so to explain why you added that extra part on there. Oh, I didn't want to.
Oh, not coming back.
So this is what's called constant curvature. Okay? Oh, yeah. Constant curvature. Because on the plane, what else can you get? If you, on the tricycle, if you're not moving your hands. Besides a straight line, you might be going in a circle, right? So the circle also has constant curvature, but there are not very many things that have constant curvature. So that's an important characteristic of the straight line. This is constant curvature. But that's part of what we need to get at. Is not only has constant curvature, but it has no curvature.
But what if your front wheel is wobbly? It's always going back and forth and back and forth. Would that be a straight line?
Bad tricycle? No, it
In
has to be a
addition
good
to your
tricycle.
arms, you also have to have that wheel has to be
Yeah,
constant.
sure.
You gotta have tight bearings.
Yeah, this is an idealized tricycle.
Yeah.
And in free space, there's another curve that has constant curvature. That is in free space. Besides, helix. So besides a circle and a straight line, there's a combination of a circle and a straight line, which is a helix. So that most springs, like car springs and other things, are helical. So a helix has constant curvature also, and that's one that never comes back to itself. So if you're, so if you're driving a tricycle,
Or a truck.
so spiral parking ramp. So but anyways, constant curvature is something that's important about a straight line, but we also need to get at then which constant we're talking about, and somehow zero curvature is what we're after for a straight line. It's the constant zero curvature. Okay, and analytically, this gets into then the domain of differential geometry or curvature. We often, if the curve is expressed analytically, calculate the ways of calculating the curve. Okay.
Loop back over there.
Was that what you?
No, that
what do you think for a good
We had two answers that weren't up there. One was if you're a bicycle, it's a variation of tricycle. If you're on a bicycle and your front and back wheels make the same track, then you're going straight. And because if you bend, in fact, the tracks diverge. You can tell when you're bending. And a variation of that one of my students gave me when we talked about that was if you're walking down the aisle at a wedding and your train isn't catching on anything, you're going straight. Because if you bend, it's going to catch.
Right. One thing, and that's a way that you can, that's a way you can check in practice. If you have a straight line and you walk along the straight line trailing, a bridle wagon, a bridle, what do they? Train, or just a string. If the string stays on the line, then you're going straight. But if it goes off the line, that's the way you can do practice. And somebody told me I don't do water skiing, but apparently that's a trick that's used in water skiing, so that if the skier falls off or drops hold of the rope when you're water skiing, well then the boat has to come back and get the rope to you so that you can go on again. But clearly the boat can't come straight over you. That's defeating the purpose. So somehow the boat has to get the line to you without actually going on the straight line that we need to do that. So you use that. So if here's the swimmer, see, we're looking down. So here's the skier in the water. So if the boat goes on a line by and then starts turning, then as with the boat's going straight, the rope is going to be pulled directly behind the boat on the path. But when the boat turns, then the rope is going to move inside off the path the boat's on, which is exactly what you want. You don't want the rope, because you don't want the path of the boat to be going to the skier, but you want the rope to. So actually, you have to turn before you get to the skier, and then the rope will go across the skier, and the skier can grab it, and off you go. So that's a technique used there. So that has to do with that, with these symmetries. Now there
was one other one we had for in space. If you had a gyroscope, and you would simply watch the gyroscope and see if it was twisting in the frame. You didn't have to see anything else; you would know what you were going to say.
Right. And so and airplanes actually use that for guidance. Because a gyroscope has the mechanical property of keeping its same direction, and of being what we'll call later parallel transport. It actually always keeps the same direction. So you can use it instead of you're going on a straight line. Okay, so there's some more. Yeah.
I guess the purpose of this discussion is to lead to questions that you will have more extensive discussions about how to define them.
Yeah.
For instance, you would point out that the straight line is a relative thing, it's not an absolute thing. If you're a pilot flying from New York to Tokyo, for instance, the route you will take will be different from when you look from a map, for instance. And when you look at the globe, you will find out what is the property of that route here you will take.
Right. So that's what we're going to want.
So that's minimum distance, but it's also a relative thing. It's a strictness relative to the ambient space.
That's right.
That will lead to spherical geometry and the hyperbolic geometry.
Right.
We'll see that in the beginning.
That's the idea. Right. And to see the properties, because we're so used to this from school, being told that the straight line is the shortest distance. But that turns out to be false when we start going into other circles. And so we need to, and anyhow, just from what you've been saying, don't you see the difference between the shortest difference? I mean, there's a difference in feeling or in notion, meaning, and what's going on between shortest distance and these symmetry properties. And we know in the plane that they coincide, that the straight line is, the line that has the symmetries is also the line that's the shortest distance. But there's a very different feel about it, because it's possible to walk in a straight line without knowing where you're going. And it's, and you don't normally think about that in terms of shortest distance. Now, sometimes you actually want to go somewhere and you want to get there in the shortest path. But there are other times when you just want to go straight. And they have very different feels. And so that's this going straight, in the sense of not turning, the symmetries of the path that you're going on. That's, then that's what's important. So there are two different notions.
We also discussed some of the limitations of paper folding. On the one hand, if you fold a piece of paper on your table or on the blackboard, you're really intersecting two planes. You have to have a plane to start with to get the intersection of two planes to be aligned. So that assumes that you have straightness in a higher dimension. If you take your piece of paper and you pull it like this, just in space, as you fold it, sometimes it's straight and sometimes it's not. If you use 2 fingers and a thumb, you can put a bend in it quite easily. So you're kind of back to the string idea there. If you have equal tension on both sides of both pieces, as you're pulling it will be straight, but it's quite easy to fold the paper curved.
We have.
No, let's see, maybe it's down there. There.
I folded.
Oh, you do. Well, this is, if you don't go down too far, and you're really doing a little different with, see, I'm just creasing it along the edge so that I'm not getting that parallel.
Okay, so that's a good example. Okay, so there's a fold. That's clearly a curve, but of course if you try to flatten it all the way over, it won't work. So if you're too local here, you can. But that's sort of like that. If you look at it, if we have what we call smooth or differentiable curve, what is the property of this? That if we zoom in on any part of it, eventually it's indistinguishable from being straight. So presumably this method, that sort of local folding, will give us a smooth curve. Certainly that is a nice smooth curve. And one could call, in fact, it's equivalent to the normal definition of differentiability to talk about infinitesimal straightness, if you wish. Okay? If you zoom in, eventually it becomes indistinguishable from a straight line. The actual epsilon delta statement is in the book if you want to make it precise. But so that's sort of an infinitesimal property. But the other thing about
I don't think this is smooth. I think it's more piecewise line, piecewise line. I think what's happening is you're doing little straight bits and then it jerks and turns the sliding out as you apply unequal pressure. So you're getting maybe 17 lines joined up that looks like a curve, but I'm not so sure it is smooth.
Oh, because you were just doing it little pieces at a time rather than running your finger along?
Well, you think you're running your finger along, but in practice, I'm not sure.
Yeah, I just attempted to fold a piece of paper without using the flat table, and I started pulling along, and now doing my little sliding test, I realized I haven't folded a straight line here. It's slightly curved.
Okay.
So in folding the piece of paper, I have used something that I assumed was straight or flat to do it.
Oh, but if you take the paper without putting it on the table and fold it over so that the whole paper is on top of the
I think if you start with the 2 edges at the bottom, and that's their perpendicular bisector thing, actually. I think if you start with those together and have somebody else kind of gently pull it, smooth it down.
That assumes a lot.
Isn't that using the straight?
Well, okay, then how about
Otherwise,
Okay, then how about using their just one point and making sure that the distances stay the same? That wouldn't assume anything.
there we go.
How about that? That's better. Just keep that
I feel
point.
better about that.
That's using her idea of the perpendicular.
So
How,
Yeah, I feel
a
better.
little better?
what's important here is that this plane, you know, on the one hand, you know, on the one hand, we sort of have this, we know that for a straight line, that it's local in the sense that we can talk about something being straight, you know, this being straight, and whether this segment is straight has nothing to do with how the line continues. I mean, this whole line is not straight, but this part of it is straight. Okay, and we talk that way all the time. So straightness is a local property, but you can't make it too local. I mean, that's the whole point. If you look at a small piece here, and you look at it small enough, you're not going to be able to tell the difference. And anything we do physically has experimental error. But that's the, and likewise also, saying over here, even if you have if the angle here is, the exterior angle is small enough, sometimes you can't tell the difference between variables. In fact, these computer graphics programs, most of them draw curves as, well, that's not quite true now because they're, that's actually a different programs coming up with the current computer graphics because of the pixels and so on. But anyhow, but when you make a slight turn, you can't tell if that is beyond your vision. Okay, but we do know that straight lines have symmetry. So I mean, that's an important part of straightness, the symmetry and this shortest distance. Now there's some other symmetries that some of your groups came up with that haven't been brought out yet in this discussion, so let's bring them out. What other ones did you find? Now this group over here found some.
Translation symmetry.
Great. So there's translation symmetry.
that one's actually like Walter's.
It's down here, actually, if you want this. Translation
Okay.
along itself. Now, so you could say rigid motion along itself. The circles also have the property that you can move them along themselves. Constant curvature is what you need for that. And that's why circles are nice for anything that's moving around, like wheels. And helixes are important for screws, so that they'll move along themselves. So it's constant curvature. But that's an important thing about straight lines, is that they move along. And usually we use the word translation when it's along a straight line. And then otherwise we call it a rotation around a circle. Okay, now what another symmetry of straight lines?
Top.
What?
Top turns.
Yeah. So there's a half turn. Okay, so straight lines have half turn symmetry. And that's important for these straight lines. And half turn about any point. And there's another important one that several groups came up with. Aha, okay. Rotation along the line. In space. I don't have one right here. But that's one of the ways that if you play pool, one of the ways of checking whether the pool cue is straight is to twirl it, and then to see if it wobbles.
How you check a push rod on an older engine. If anyone ever worked on motors or anything, a push rod, you always roll them on the table to see if they wobble.
It's the same with drumsticks, so you roll them across the floor and see what happens.
So that's more accurate than sighting along, and because a little bit of wobbling you can start seeing. Okay, so that's rotation. Rotation around itself. in free space. And then there's another reflection symmetry that we did. Several groups brought up. So besides reflecting in the line, you can reflect perpendicular to the line. Right?
Yeah.
Circles also have that property, that you can reflect in a diameter of the circle itself. But straight lines have that, and that's another part of important symmetry in straight lines. Okay. So the purpose of this is just to get when you're thinking about what straight line is, and it's not the whole notion of how to formalize this is a very complicated thing, and it's traditionally the subject of differential geometry to actually formalize this notion of straightness, and we normally don't do it in any of our math classes to even talk about it because it's difficult to formalize, and I think that's a mistake. I think we should talk about things even when they are difficult, because they're important ideas that people at all ages can understand. I mean, most of the discussion we've had right now is to be understandable by elementary school kids, and so they wouldn't have any trouble contributing to the discussion. And the symmetry properties are very important. They're very important properties. It's very difficult and impossible to make this into a usual formal definition, but that's okay. And I would suggest my urge is not to worry about that. So that it's better to do this than it is to just say, well, we know what straight lines are, or we're going to define them to be this in certain circumstances or whatever. Okay. So now it's time. Let's take a break, and then when we come back from the break, then we're going to do exactly what somebody here suggested, is then apply this to other surfaces. And so we now have some notions of what it means to when we experience something straight. So now we can talk about what are the straight lines on a sphere, or what are the straight lines on a cone, and so on, rather than doing what some folks do, is to actually define the straight lines to be the great circles. And I think that's not right. I think we can make convincing arguments that it's the great circles that are the straight lines, as opposed to defining them. So that's what we'll do. So let's have a little.
But hot.
But hot.
Oh, yeah.
I look like a beach. You're suffering, in other words.
Okay, now, I'm going to, go quickly over some things that I would spend longer on in class. But here's a little, this is a little model of a cone. Call this a 450-degree cone. Now, I would have the students make their own, but just to save time, I had a bunch that were made up. And this is a common kind of corner that you can find, on the walls and in rooms around. And there's 450-degree cone because there's 450 degrees around the center point. And even though you may not want to call this a cone because you can't eat ice cream from it and so on, but you can, if you ruffle it in the right way, you can even eat ice cream from it if you want.
A waffle cone.
So you can do,
Seen those.
if you waffle it,
Yeah.
Do it this kind of way. But anyways, this is a cone. Now, we want to talk about what's straight on this cone, and the point of view that we want to take now is intrinsically, not from us looking from the outside, but a bug crawling around the surface. What would the bug experience as straight? Okay, so what is straight just with respect to the surface? And of course, we're like that on the Earth. We're like bugs crawling around on the Earth. So, the point here, just to make some things go a little quicker if we flatten out this piece of paper, then this line, these lines that I've drawn on there already for you, are straight. When it's flat, so if I then bend it, it's no longer extrinsically straight from your point of view, looking at it from the outside, from our point of view. But from the bug's point of view, from the surface's point of view, nothing has changed. I'm going from this to this. So this is still straight. And if you wish, you can use the fancy term geodesy. But I think it's fine to also just say it's straight with respect to the surface. Intrinsically straight. Obviously not straight free space. Not extrinsically straight, but intrinsically. Is that distinction clear? Okay. Think of a bug crawling around on the surface. Okay, so now what I want you to do is just to spend a little time looking. There's most of a quadrilateral drawn there. There's just one side to complete, and you can complete that side. I couldn't complete it because the copy machine didn't want to, wouldn't copy the whole thing. So, but you can complete this quadrilateral, and then then I want you to draw in the diagonals of the quadrilateral.
So, I'm afraid to do anything without. So,
if you mess one up, I've got spares.
Okay, yeah. Okay, so. There's our
thing that it was easy to find shortest paths that went across the diagonal. It's relatively easy. And then you can convince yourself that the shortest path is to go to the center and then back out again.
Yeah.
That's the shortest. So if that's your notion of straight, well, then those are the straight paths. But none of those paths had the symmetries. In fact, I don't think any of them had any of these symmetries that we talked about. So even though one of the paths had 180 degrees on one side, but notice, it's very careful here to say half turn, not 180 degrees, because it's really that half turn that's the important thing. But because what is it? It's from A to, if you draw the diagonal from A to C, or the path that goes to the center and back out again, it's 180 degrees on one side, but then it's way more than that on the other, 125 or something on the other side. So, because more than that, right?
270.
Yeah, 270. Yeah, I think so.
Yeah, 180 or 270, right? Okay, it's 270 on one, 180 on one side, 270 on the other side, right? So it clearly doesn't have the bilateral symmetry because the two sides are different. The right and left. One way to think about it is the right and left legs of the bug. If the bug's going straight in the sense of not turning, you would think of the right and left legs going the same distance. And so this is an example of where the shortest path is not straight.
That's not the shortest path. If it is the shortest, it has to be straight.
If that's your definition.
If the shortest path?
The shortest one has to be straight.
Why?
Because you do a local variation. Ask yourself.
The differential geometry.
Can I be just a little bit?
But
that's probably a candidate. That's not the shortest one.
well, it turns out that theorem, there's a theorem in differential geometry that the shortest path is straight, but it doesn't apply at this.
Singular.
Because it's got a singular point.
Because
Not differentiable.
In fact,
Gotta be different.
this is a very interesting thing. I mean, it's possible to fold this. Right? You can fold these things. And then there is a path that has symmetry. Right? I mean, where the two sides are the same. And that's the whole point about folding. The two sides are the same. And of course, there's all the same problems you got to fold carefully. And you really have the sides the same. Okay. Now, do you remember, now one of Euclid's postulates is that all right angles are equal. I think it's Euclid's fourth postulate, which I don't know about you, but I always thought that was really silly. How in the world could it possibly be that right angles are not equal? Well, here's the example. Because what is a right angle? According to Euclid, Euclid defined a right angle. If you go back and look at, a reasonable translation of Euclid, he said if you take two straight lines so that they intersect, so that all four angles are congruent, okay, then those are right angles. Well, let's do that here. Here's so you can do that on your thing. There's one straight line, straight in the sense of, either in the sense, this is straight, both in the sense of shortest and in the sense of really having symmetry. And then move it the other way. So there's another one. So there's two straight lines intersecting so that all angles are congruent. So on this surface, that's a right angle. Now, of course, at other points, right angles are a little different. So this is a surface in which all right angles are not congruent, are not equal. Now, I don't know whether I like to think that Euclid was actually thinking about cones like this. So there's other right angles, and they're not congruent. So this does not satisfy Euclid's fourth postulate. And it shows the need for that postulate somehow. And Euclid did examine the geometry of cones and cylinders. Some of this was lost. Some of his work on this, but some of it does exist. It's been translated into optics, where there's a lot of work on cones and spheres that Euclid wrote. And so I don't know. I mean, it's possible that Euclid was actually thinking about things like this when Euclid wrote that postulate. I don't really know. I don't know that. I haven't seen any historical evidence, but it's possible. Okay, so that's, now, roughly, the theorem. Yeah.
What were you saying was the straightest path between like these 2 points then?
Oh, I didn't say. No, I didn't. I just said that I said that it's possible to convince yourself that going to the center and back out again is the shortest.
Okay.
But in the sense of symmetry, there is no straight path.
Between some pairs of points.
Okay, between some.
Right.
All right, some.
David made a straight line, but
Between
that kind won't necessarily connect 2 points unless they're symmetrically located.
But now there is,
respect to
here's the,
So I got one of these short
Here-
things here.
here's the theorem from differential geometry that's being alluded to, and that can be stated in the terms that we're talking about now. If all right angles are equal, and if all straight lines, that is intrinsically straight, so intrinsic or geodesics, intrinsically straight lines can be continued indefinitely. Now that was another one of Euclid's postulates, that every straight line can be continued indefinitely. Forgotten which number it was. So that just means that there are no holes or edges. And so, of course, on this piece of paper there is an edge, but we can imagine this going out indefinitely, forever. Okay. So if we have these two hypotheses, then the conclusion is shortest path is always straight. So, and this is an example to show that you need this first hypothesis. Huh?
And the second.
And the second one?
If you join B to the apex, to the cone point, it's hard to know where to continue.
Say again,
If you join B to the cone point, and you try to decide how to continue it, it's not true.
You could use a symmetry. I think you could use the symmetry.
Use the folding.
Use the folding.
Yeah, so in terms of symmetry, there's always a continuation through the cone point.
It's just a weird one.
Right? Weird.
But it's weird because if you flattened it one way, the 180-degree one, and moved the line real close, from outside, it just feels like, well, that would be walking straight also.
But in terms of symmetry, I can go from C to the cone point, and then they continue straight. I think you can find by folding. So there is a way to continue straight. But unfortunately, it doesn't get to either A or E. So, yeah.
We found out in this group that we need to come up with two definitions for a straight line. If you can see the other point from A, if you can see B from A, then just go straight. That's the shortest distance. If you can't see the other point, you have to go to the vertex and then down. And that's not always, and that's the shortest distance, but not a straight line in the sense. But we also found that it's possible to ruffle the cone in a way that, for example, if I ruffle the cone in a way that if I'm at B and I can't see D, I may have to go through the vertex and down to B, and that's not the shortest distance. I don't know if I'm clear.
Yeah. If you found another point that you couldn't see from A.
We found another point you cannot see from A, so you go to the vertex first and then down to the point, and that's not the shortest distance.
It's not the shortest?
No.
Between the two.
Sure.
On the surface. You see, it will ruffle. You see, for example, if you ruffle it like this, all right? Okay, say A and D now. You're at A, you can't see D. Okay?
Okay.
Not
Right.
for the quadrilateral,
Right,
you get
right,
a
right.
new point.
Yeah.
Depends on seeing.
I get what you mean.
In terms
Yeah.
of seeing, think for these surfaces, it's better to think in terms of the bug, not a bug with eyes, but a bug with feelers. These feelers up front, and they're feeling vibrations on the surface. And one of the things you can do when you're wandering around the outside here this week is to look for water striders. I don't know if you're all familiar with water striders. They look sort of like spiders, but they're not spiders, they're insects that walk on the surface of the water. And they're very much like the kind of bug that we're talking about now. They seem to only have a two-dimensional perspective. I mean, their universe is two-dimensional. It's the surface of the water. Now, of course, it's hard to get the surface of the water to be shaped like this. You can't test this out. But if you find water striders in any, along little side pools in these streams or along Beebe Lake, you should be able to find some. They're out now. And these water striders, they're going along the top of the water, and if you're very careful, you can actually go down with your finger and touch them. And they don't know your finger's coming. You have to go move slowly because they're very sensitive to any vibrations on the surface of the water. So if you move too fast, you're going to move the air, which is going to disturb the water, and then they scoot off. But if you move slowly enough, you can actually touch them. And fish use that same technique from coming below to eat them, if they can do it without disturbing the water. But you can also take one and then disturb the water a long distance away from the strider, and you'll see that it notices the vibrations on the surface of the water. So water strider is a good example that you can see. But think in terms of the seeing is vibrations along the surface. Because the point is that we want this to be intrinsic. So you want to, and think of so imagine that you have again an ideal surface and the vibrations are now flowing along straight lines on the surface. Okay, so straight is not shortest. And also shortest is not straight. And whereas straight, I'm using straight now, and I think it makes sense to use straight in the sense of the symmetry property, or not turning. And that separate these as two separate notions. And now we're seeing they really are separate notions. It's just in the plane they coincide, but that's then a theorem in the plane. But if we have this, if we have all right angles are equal and all intrinsically straight lines can be continued indefinitely, then I didn't write the conclusion. But the conclusion is that all straight lines, all Shortest lines are straight.
Intrinsically straight.
What?
The conclusion is.
All shortest lines are intrinsically straight.
But it's always true that intrinsically straight are the shortest distances between two pairs of points.
What's your
No,
definition of straight?
not necessarily.
If they're close enough together.
Right.
Okay. So the example that some of you already, the example is on a sphere. Now, if we do the same thing on the sphere, you can, the great circles are the ones that have the symmetry properties. They have all the symmetry properties when we're talking about a straight line. It makes sense to call them straight with respect to the sphere. Geodesics on the sphere are the intrinsically straight lines on the sphere. These great circles. But if we have 2 points here, say on the equator, one straight way to go from this point to this point is to go this way. So that's straight, but it's not shortest, obviously. Shortest is to go this way. So straight is not necessarily shortest, but shortest is always straight. And straight is always locally shortest. That is, for points that are close enough together, that's the shortest. So that's the continuation of this theorem. That's a theorem of differential geometry. What?
What's that?
Shortest? Shortest is always straight.
On that surface.
On a surface with all right angles.
On that.
And every straight line can be continued indefinitely. That's true for the sphere. The sphere has that property, all right angles are equal. And because the sphere is homogeneous, every point in the sphere looks like every other point. So it's,
By the way, indefinitely may mean that it comes back on itself. That's okay.
right.
Careful with that, because that you may think of indefinitely as really off to infinity, but the theorem holds on the spheres.
Yeah.
How did you define straightness on the surface? What was your definition of straightness?
Well, for these surfaces, the symmetry properties here, not turning symmetry, but it has the symmetry. Locally and intrinsically, symmetries of a straight line. Okay. So now, of course, for a more arbitrary surface, then you have to refine that definition, because if surfaces don't have enough, if they're not uniform enough in these surfaces we're working on here, then we have to, and that's the subject of differential geometry, which we'll talk about a little bit later on. Okay, but for these surfaces, the surfaces we're dealing with now are more regular, uniform surfaces. And here's another example. This is a model of the hyperbolic plane, and it also has the property that all right angles are equal and straight lines can be continued indefinitely, and you can fold it. So don't fold this one, but it's theoretically possible to fold it. I just don't want this one folded. This one's barely holding together now. It's 10 years old now. And this is and this can be continued indefinitely. So this is a nice paper model, and it's very easy to make, but very tedious. So you just make it. Well, there's a description. It's a description in the book, and you're gonna, and you're gonna get something else later in the week that'll have a more accurate description of just how to make this. So let's come to now, but it's made out of little angular strips of paper, all identically the same, just taped together the only possible way they can tape together. You can see them here. Now, talking about theorems, the way that analysts can sometimes confuse us is that there's a theorem that's quoted in a lot of books that says that it is impossible to embed the hyperbolic plane isometrically in Euclidean space. That's a famous theorem that's quoted a lot. Well, here it is. Here's the hyperbolic plane isometrically embedded in Euclidean space. Right here, I've got it. What's been left out of the statement of that theorem is that the actual theorem is that it's impossible to isometrically embed the hyperbolic plane in a C2 fashion in free space. And since analysts always think about C2 anyhow, they often just drop it off. So when this thing is sitting here in free space, there's always going to be some points at which it's not, sorry, not even C1, just not even C2, just C1. There will always be some points where it's not smooth, not differentiable. But it's still here, and it's still asymmetric. And the easiest way to see that is I take this surface and I flop it down like this on the board. There we go. Here's the surface is tangent to the board along some circle going around here, but it's, I mean, it looks like it's tangent, but it's not actually tangent because these ruffles, you see this ruffle comes straight in. So this curve here is not tangent to the board. So it's not differentiable. And directional derivatives don't all exist, and so on. I mean, you can actually relate this to calculus if you want. But the so that's the theorem that if you make this thing, there are always going to be ruffles. But it's still a nice surface, and you can continue it indefinitely. I would love to have a more durable version of this, bigger. Okay. So now we have some examples of non-planar geometries. We could say non-Euclidean, although after one of Maria Terrell is going to come in and talk about her work later on in the week, on Thursday morning. And she's going to talk about the fact that it's a little inaccurate to call it non-Euclidean because Euclid did study spherical geometry and geometry on cones and so forth. But it's certainly non-planar and non what we normally call Euclidean geometry. Okay. Well, what I want to do now, I want to give you some homework to think about, and what I want you to do, just to get some experience of what the students go through, is to actually write out, but work together. You know, it doesn't have to be the same groups that you have now. It doesn't have to be groups of 4. However you want to lump together. You know, just to help each other out. Look at side angle side and angle side angle. And decide. Now, let's remind us what side angle side and angle side angle are. I'll try to, let's see, what I should do. Maybe we should. Maybe what we should do is to drop off a set of these spheres over the door. So there'll be some over there we can use. So by angle side angle, side angle side. So this is that if we have a triangle,